Today we're looking at rotational dynamics, and we're going to do assignment 38, and we're going to do problem 34. Now what's interesting about this problem is normally on the AP test you could easily do this problem using conservation of energy, but we haven't done that yet. So this is showing doing it a different way. So I'm going to write down my given because there's a lot of information in this problem. So it says a 2.4 kilogram ball, so the mass is equal to 2.4 kilograms. Now it's a ball, so the reason that it's a ball is the shape has something is important if it's rolling, because it has to do with the moment of inertia. So a ball is a sphere, and I know the moment of inertia of a sphere is 2/5 mr squared. It has a radius of 20 centimeters, so when I write down the 20, the first thing I'm going to do is I'm going to convert it to meters. 1, 2 is 0.2 meters. It moves 5 meters, so x is equal to 5 meters along a 37-degree incline, and that's one of the only angles that, again, they use on the AP test. The coefficient of friction, our mu sub s, is equal to 0.3. and mu sub k is equal to 0.2. Using torque, force, and rotational kinematics determine the ball's velocity at the bottom of the incline. So the reason it says that is using actually conservation of energy is easier whenever we have a change in height. But we're going to learn to do it this way because in case they ask us questions or in case they specifically say work it this way, you want to know how to do it. All right, so the first thing I'm going to do is I'm going to draw a picture because I want to see what's happening. So I have an incline, and the angle is 37 degrees, and I have a sphere, which is a ball, that's going to roll this way. So the direction it's moving is important because I always want to establish my sign convention. So my sign convention, the direction it's moving, I'm going to call that positive, and this way is positive. So that's my sign convention, perpendicular and parallel to the surfaces in contact. And I'm showing the direction that it's moving. Now, what I'm going to do is, because I'm using kinematics for this, remember that rotational dynamics has to do with torque is equal to I alpha. But we also learned torque is equal to Fr. So what we're going to do is we're going to combine these two together to figure out what we need to do. So if I look at this, let me draw my free body diagram. Now a lot of times on the AP test, they're going to specifically tell you if you have to draw a free body diagram to draw your forces at point of contact, not at center of mass. So the weight acts straight down like this. If the object is moving this way, the frictional force acts here at the bottom, that's point of contact like this, and the normal force is also going to act at the surfaces in contact, so the normal force would act like this. Okay. So again, where do I start with this problem? Well, I know that, first of all, there's a difference. This ball is rolling down an incline. Okay, so if this ball is rolling, what is causing it to roll? If there was no friction, the ball would slide. So what is causing this to roll is the frictional force. So the friction causes it to roll, which means that the frictional force, F of F, causes the torque. And this is important because when I say torque is equal to Fr, that means torque is equal to the frictional force times R. Okay. Now, basically to solve this problem, I'm going to say that these torques are equal to one another. So I'm going to get Fr is equal to I alpha. Let me start with summing forces. Let me find this F of F. So what I'm going to do is I'm going to say summation of F is equal to MA. Now I'm going to look at my free body diagram and say what are the forces going in the direction this is moving. Now the problem is this weight is not going perpendicular or parallel, so I have to take my weight f of g and break it up into the components. So I have here FGY and FGX. And when I look at my diagram, I see FGX is equal to FG sine of theta because it's opposite this angle. So now when I sum forces, I'm going to have going this way FGX, which is going to be FG sine of theta, minus the frictional force is equal to MA. Now remember, when I'm ending up using the torque, I just want the frictional force. So I'm going to rearrange this, and instead of FG, I'm going to say MG sine of theta minus MA is equal to F of F. So that's what the frictional force is when I'm going to calculate my torque. All right. So now we know I'm basically going to say this frictional force times R, because that's torque, is equal to I alpha, which is equal to torque. Okay? So now I'm going to say mg sine of theta minus ma. Okay, so all I'm doing is substituting this in here, times R is equal to, so now I'm going to put in the moment of inertia of the sphere, which is 2/5 mr squared, times alpha. Now, if you notice, this is all linear quantities. I have R, I have A. So instead of putting alpha, we know that A is equal to R alpha, therefore alpha is equal to A over R. So I'm going to substitute that in for this. So now I know this is equal to A over R. All right, so now this is just simplifying this. Now instead of me plugging all the numbers in, even after I simplify it, what I'm going to do is, until I get my final answer, I'm going to leave everything in terms of variables. And the reason I'm going to do that is, a lot of times now on FRQs, they don't give you any numbers. This problem has numbers, but they don't give you numbers, and we want to be able to rearrange it in terms of just variables in case they ask us that. So now when I simplify this, first of all, I can cancel the m's. So now I'm going to have g sine of theta r minus ar is equal to 2/5. And what I'll do is I'm going to cancel this with that. So I'll have 2/5 RA. Now there seems to be an R in each variable, so let me cancel that out. So now I'm going to have g sine of theta minus A is equal to 2/5 A. So I'm going to move this A on the other side. So I'll have g sine of theta is equal to 2/5 A plus A. So now I'm going to fraction. So remember, A is really what? 5 over 5. So I'm going to have g sine of theta is equal to 7/5 A. And since I want to solve for A, I'll put the fraction on the other side. So 5/7 g sine of theta is equal to A. Now I could substitute that in and find A, but right now in terms of variables, I'm just going to leave it like that. What I'm solving for in this problem is I'm solving for VF. So I know V naught is 0 because it starts from rest. I want to find VF. I just found A. Remember, here's A. I know A is equal to 5/7 g sine of theta, and they told me X is equal to 5 meters. So which equation has that those four variables? So VF squared is equal to V naught squared plus 2AX. So VF is equal to the square root of 2AX. So VF is equal to the square root of 2 times 5/7 g sine of theta times 5 meters. So now I'll substitute in, I should have put the angle in. So 2 times 5/7 times 9.8 meters per second squared times the sine of 37 degrees times 5 meters. So now when I put all this in my calculator, I get VF is equal to 6.49 meters. So the key here to doing this problem was it's the frictional force which causes it to roll, because that's creating the torque. So when you say torque is equal to torque, it's the frictional force, not the net force that's acting on that. And that's it.